Okay. If you didn't see last week, I'm hoping you did, but
Well, not last week was just the chat, right? We just had the bit of chatting.
oh, right. I meant the week before. Very good point. So I'm going to do screen 3 so I can just put things over there. Here. Oh, excellent. I feel like I'm learning a new thing about Zoom every day. Okay, can y'all see that okay? Should I zoom in on that any? Or is that good enough? All right, good. Now, you remember last week, we went through all the math about how to get the p-values for, and this really is a type of hypothesis testing where we're getting the p-values for a coefficient from linear regression. And then we saw how there's some tools that do that for us. Behavior. My notebook's acting quite frozen at the moment. Oh, there we go. All right. Now it's working. Well, then I just wanted to ask y'all, hey, what do you think about using p-values to find collinearity? So what are we going to do? Well, we're going to add a fourth variable to the one we were using before. And this will definitely cause collinearity between X2 and X4. And of course, in our fake data model to create our labels, we're not going to use X4. And we should see a collinearity. But look at this. The coefficient strength between X2 and X4 is kind of divided. What did we expect? We expected to see 3 for X2, but between X2 and X4, what do we get? We don't get anywhere near 3. Here's 2, here's 4. This should have been 3, but look how it's divided its strength between the two. And do we get any indication from the p-value? None. Now remember, we're blind. In the real world, we wouldn't have known these weights should be the way they are, and that they would be off from what we defined by a certain amount due to the noise that we created. But literally, we could not tell using p-values that there's collinearity here. So this is just a way to say p-values aren't going to help us for that. They're going to help. They're going to be very powerful, helping you know if a coefficient is worthless, if a feature weight is worthless. In other words, excuse me, if including a feature in your model is valuable or not. But they're not going to help you with collinearity. Now, in my preparation for this week, I apologize. I should have added lasso. I didn't. So we'll begin with that next week. And then we're going to go right into feature engineering. And then we're going to do some PCA again, even though we visited that a little bit. And then we're going to do some real modeling and look at some metrics for that. And then Geith is going to do all the same cool stuff, but for classification. So in this work here, I want to just show, and I believe we might have been through this before, but it'll be good for us to revisit it. I just can't remember if we've done this in class yet. So finding and removing collinear features. We're going to look at some things here. I'm going to define 10,000 points, and we might want to change this. In fact, you know what? That's just going to be too busy looking. So we've got our number of points here. That was to prove a point before. And now I've created these fake features, but you can see, even though I put some weights on X1 and X3 and done these quarter rate powers. It's amazing. That will still be collinear between X1 and X3. And we'll see that here in a minute. So we're going to stack these together. I haven't put X7 in there yet. And then the real model depends on X1 through X5, as we've seen, but I'm not including X6. Again, we don't know what is the best model for the labels, but in God mode, forgive me, God, I don't mean it quite that way, in all-knowing mode, it's a spirit of, okay, we're trying to understand more by being the creators of the output data. And then we add some noise to it here. And by the way, you can get to all this in our normal Google Drive folder that I've been sharing with y'all. Okay, so now I'm gonna just create the data. I'm gonna put the labels here at the end. And notice I've included X6, so I'm gonna name them accordingly in a data frame. Now, I think we've seen this before, Pearson's correlation coefficient calculation. And this related to a series I was doing on LinkedIn too. But the reason I like to put this in a data frame is because I'm constructively lazy. I really like Panda's correlation function here. It'll do all the correlations on a data frame. And then the rest of this stuff is literally just the fancy stuff to do this heat map or these value maps for the same. So run that, and I see that, oh no, when I see, hang on. Okay, so this is the correlation map that I just created. And we see good correlation strengths over here as expected. X6 is kind of low though. And you see these values here. Now, what did I expect X6 to correlate strongly to? X1. But I've got this kind of weak right here. But still, I just wanted to show, yeah, still then, X6 to X, oh, I'm sorry, there's the collinear. Duh. Okay, so, and it's pretty strong, even with that low power of 0.25. So we see that X1 and X6 are collinear, but which one should we remove? Now, we know we should remove X6, but we can't really trust this value to tell us that. So what do? Well, we check our model weights from training a model before removing a collinear feature. So what do I mean? Well, I'm just going to call the linear regression class, which I've already imported above. And I'm going to look at various values. So I just want to look at R2. Now, if you're not, excuse me, R squared. If you're not familiar with R squared, it's just the strength of a model, and it's going to show us the coefficients we get. Here's X1, 2, 3, 4, 5, and notice I made the coefficients come close to their X labels, and then 6. So I run this, and in this case, because of the way I did it, close to 1, close to 2, close to 3, close to 4, close to 5, and then boom. Which one do we take? Now you can see in this case, wow, X6 even got a stronger coefficient. So we can't judge it that way. So what do? Well, I'm going to do this manually first. I'm going to remove one at a time. So you see, in this case, I've removed X1. And in this case, I've removed X6. So we'll look at, okay, just waiting. Thank you. And then now I'm creating a new data frame so I can do, so this is without one. So we'll create that one. I think I need to reboot my system, guys. Okay, so this is without one. And well, what is that? This doesn't really tell me much. It can tell me when collinearity is present, but this really isn't telling me much. So now I'll do it without 6. Really, by looking at these two maps, I can't tell which one I should keep. In other words, it's hard to tell which feature is best to remove from only looking at correlation maps. And by the way, this, I don't think this one is in our folder yet. I'll make sure I put it there. So what we have to do is check our model accuracies after removing each collinear feature and then after model training. So here, look at what I do. I've just got 2 groups. Y actual is just this data frame I've been working with in the last column. But in this case, I keep 1 through 5. And in this case, I keep 2 through 6. And I'm checking both cases and then looking at the R squared and the R squared adjusted. Now, just so you know, R squared is a standard thing. R squared adjusted, we can get that by doing this calculation. Sorry for that confusion. That should be indented some so it's clear. Okay, now let's look at this. With features, oh, this is misleading. With features 1, with features, oh, yes. This is with all 6 features. And notice the score here. These are pretty tight because the fake data is so good and clean. But notice that this R squared value and even this R squared adjusted, well, excuse me, let's look at just the R squared first. This R squared is greater than this one without X6. And it's also definitely greater than this one without X1. So why is this R squared better? And then let's look at the R squared adjusteds. This one's greater, the greatest, this one's the least, and this one's the worst. So if we didn't know better, we would be inclined to keep all 6 features, right? Because it had the greater accuracy. So here's a trap to avoid when you're doing this method. This is what I'm getting at. Do not fall into this trap. We knew there was collinearity. Now we need to compare between these 2, which one to remove. If we look at this, we'd be tempted to keep all 6, but we know there was collinearity present with all 6. So we have to choose the better between these 2. This was overfitting, basically. You can add more features to just fit. Yeah, Guy, go ahead.
Here, okay, I will say it in a strong way, but really I'm asking, I'm not correcting or something. Somehow I disagree until I'm convinced. Since the R square is higher with the whole feature, even if we have collinearity, maybe this collinearity is managing something. I will give example. And I think we discussed about it, Tom, previously. For example, if we are using the cholesterol information in predicting something, and we know that the low density cholesterol and high density cholesterol are collinear to each other. We know this is even medically proven. Okay, but we cannot ignore or drop one of them for medical reasons. So collinearity is not enough to decide that we have to drop one of these features. Not always, at least. And forget about the example. When I'm checking this number, I will suggest that this kind of collinearity is similar to what we have in the cholesterol. It might be there. It might be collinearity or maybe negative correlation, let's name it. So each one of these features is doing something toward in different way. So we know they are collinear to each other, but we cannot decide to drop one of them. So is there, now this is my objection, but my question, is there any other value can help us here? This is my question. Not only the R-square and the collinearity matrix or the heat map that we generate. I'm really here because I even personally need to have such a matrix to use.
So can you hear me okay? I think I'm having system problems and
We hear you, sir.
say again, Hugo.
It's Aziz. I mean, we can hear you.
Okay, good. When Gaith was talking to me, it was coming across garbled, but I don't think it was his fault. I think it's mine. My system's been warning me this morning that it's low on resources, which is weird because I have a very powerful laptop that has 64 gigabytes. So I'm trying to close things that might be the problem. And give me a second to see if I can recover from some of this. I do not know what would cause it because Chrome is mostly what's open, and it usually would not cause these kind of problems, but I think it's getting better. I just hate to close all these because then I have to open them back. So I'm just closing as much as I can to make sure we're in good shape. Okay, I think it's better now. Guy, I apologize. Can you re-ask that? I caught most of it, but not enough.
Okay, back to one. I will back to one example that we discussed about it previously. I will give the example just about the collinearity and how to drop one of the features. For me, when I'm checking that R-square is better with two collinear features is not enough. Knowing there is collinearity is not enough for me to decide to drop one of them. And the example I make it is something that it's already, I face it, which is the cholesterol, the negative and positive cholesterol values, LDL and HDL. We know, and it's even medically proven, not only from data, that there is collinearity between these two values. But whenever we are using values information, cholesterol information to predict or estimate anything related to healthcare, it's not acceptable to drop one of them because they are collinear in different ways. So at the end, one of them is doing positive impact and the other one is doing negative impact with the linear relationship between them. So collinearity for us, it's not enough to decide to drop one of them. Now, if we test the model and also we have the R-square, it's even better with both of the features. What kind of matrices or values that we are looking for to decide to drop one of the features? Here, the example that you give us, R-square, it's still better with both features. So do we have anything else? This is my question. Any other metrics?
Very good. It's actually, we do, but it's interesting. Even if you look at, I get the sense when I'm looking out on the edge of this stuff, even in technical publications, it's a bit of throwing up our hands because we would think that PCA could help us. But it really only helps us as well as the correlation matrix helps us. It's a different view. It's just telling us, hey, you've got collinearity present still. It's not even as good as Pearson's to show us which pairs are collinear. It just can tell us you still have collinearity present. It's a little step further than just using PCA. You have to use condition numbers on the matrices. But and if I find something, but in all my searching for writing the book, I cannot find anything better than this. Again, the other side of getting rid of the features that aren't very worthwhile to keep, that would be lasso or even ridge, although I prefer lasso for obvious reasons, which will be obvious to y'all. But this does relate to this particular phenomenon does relate to overfitting. We can actually add in false features. We can create more features to get better fitting, but it will cause a bit of overfitting in training. Last night I was working on a natural language processing problem that was quite challenging with another language. And on the training set, XGBoost got 0.98% accuracy. But on the test set, it got no better than all the other modeling methods. And in my writing that I don't trust this one as much. I don't trust XGBoost as much because it was so high on the training. Whereas some of the method that I was suspecting would do better, which was AdaBoost, the accuracy on the training set and the test set were very close. And so what I'm trying to say is don't get sucked into greater accuracy, especially when on training action. Now, again, this is training accuracy. And we're only doing this for the sake of using all the data to find the strongest indication of which collinear variable to remove. But if we had done training and test split here, which we haven't actually covered in this class, but when we divide our data between training and test, you'll see that the model is actually more accurate on the test set for those cases where we have removed one of the collinear features. In fact, that would be a good thing to add. When I talk about the lasso, I'll show a case of what I just said. But what I wanted to talk y'all into specifically in this case, and great question, guys, still. Once you know collinearity is present, don't get sucked into comparing it to this. You only really want to compare these two. Just a point I wanted to make. All right. So there it is again, too.
There's a question from Greg in the chat.
Oh, yes, let me get it. Chat. Okay, this is a great question, I think. Oh, it is penalizing you, and it's not very useful here, Greg, because it's not a big change. R squared adjusted is important for parsimony. In other words, it's penalizing you for having too many model parameters. So let me show you all that equation again. It's just this little guy right here. You look, we've got R squared, but then 1 minus R squared times the number of params minus 1. This is a concept of degrees of freedom. And then, no, excuse me, this is, yeah, this is the in, I shouldn't call it params. I think I got that from another site. This is the number of model parameters, and in params, which was defined above somewhere, forgive me, should have been down here. We'll find it later. It's the number of records, okay? So I should have made sure it was included in here. But if I'll clean up these notes. R squared adjusted is, again, encouraging you to have the appropriate amount of parameters. So R squared is not influenced by the number of parameters, whereas R squared adjusted is the number of model parameters. Okay. So here's the equation for R squared. This S total, this is the average of the Y's, but this is the prediction of the Y's. So you can see this is based on an average, the difference of each Y from the average of the Y's, but this one is based on the errors between the predicted Y's and the actual Y's. So if we have a good model, this value is going to be very small. And if there's a strong slope of some kind, this value is going to be all over the place. The average is not going to be very good. And so the better that your model gets, the stronger there is a strong correlation. If it were a perfect model, you can see this would be no error. This would be a lot of errors. So that's why it's 1 minus. This would approach 1 for as models get better and better. Now, there's 2 other ways to look at all of this: tolerance and variance inflation factor. And I'm just going to give it away here up front. Big deal. I wish the educational time and space wasn't given to these. They're really just another view to correlation when you get down to it. But let's go through them because I want y'all to know what they're about. So you've got these guidelines. 1 minus R squared for tolerance. There are no specific rules for tolerance, but there are these guidelines. So in case you ever forget, you'll be able to find this notebook in our folder of notebooks for the class. And then variance inflation factor is just 1 over T, or 1 minus 1 over R squared. So again, it's really just taking it back to what this value would have been right here without the 1 minus, if you look at it. And then the inverse of the same for variance inflation factor. Well, how do you use these? Because they are a little different. Among your features, you are just, and this is a slick way to do what I'm about to say, you've got a group of features. And in our case, there's 6 of them. Each feature gets a chance to be the label against all the other ones. And we can see that. Now, I'm showing you this because I looked at this hoping it would give me an indication, hey, which feature should I remove? And again, it isn't good for that. It just tells you which ones you should pay attention to. Well, these 2, as we suspected, 1, translating from coding numbering, 1 and 6, they're in the danger zone. These others are okay. And again, this one being high and this one, they're the ones so these are the ones in question, given the guidelines we looked at above. But basically, we see that feature indices are causing us issues due to being collinear. However, we pretend we are starting here and do not know which one is best to keep. We already know which one is best to keep. But are T and VIF helping us to know which feature is best to keep? No. So we still have to calculate R squared for the cases where each of these is removed. But this time we'll train the features we are keeping in each case and with our label. So same thing again. We're using these. Then we're using these, and we see, yep, the R squared is better when we drop X6. And the R squared adjusted is also better when we drop X6. So clearly it's best to remove X6, and this is what we expected from our work. So in summary, we applied R squared calculations on model predictions using only features for use in T and VIF calculations to indicate which features were collinear. But then we used R squared calculations still to figure out which one to drop or to keep. So accuracy is still better with X through X6. Don't fall for that trap. Again, once we know collinearity is present, we want to get rid of it. Okay, so using only R squared and feature removals to determine best to keep. Well, this is just a slick way, and you guys can play with this code later, to just, once we know collinearity is present, we just go ahead and look at all the R squareds. And you can see, wow, these are significant. Look at that. We remove any of these, the accuracy drops horribly for either of these metrics. But look how close it is for these two. And yet we can still see that we should keep X1. So in my opinion, once you know collinearity is present, you want to go straight to this. Now you could have said, well, you only needed to look between X1 and X6. Still kind of nice if it's not computationally horrible to go through all of this. Okay, now above we had, oh, I should have been running these, my bad. So we'll go back up to where I last ran. I'll run this one again. And then I'll run these real quick. I know I could just do run before, but I'm going to do them by hand to make sure I haven't induced any problems. Run this, and it did it okay. Now we're going to create a bigger stack of collinearity. And I improved the coloring this time. So now we can see X1 is collinear with X6 and X7 is collinear with X3. But which ones to keep? Well, I just did this curious thing. I did a kind of a fudge. I'm just going to use the correlation in a different calculation for this. In other words, I'm supposed to use R squared here, but I'm going to just go ahead and use the correlation coefficient. In other words, this is a tolerance based on correlation coefficient, and this is a VIF. So it's not the same as your typical T and VIF. I'm doing a pseudo one. And hey, it's helping me if I want to see things. Look at what's going on here. I've got X7 to X1. That's really, that's helpful, seeing that. Or, excuse me, it was something else. Well, I forget which ones I made them collinear to. But in other words, I can use these if I really just want a different view. That's really helpful. I find this one's especially helpful. But there we go. It's X6 to X1 is really small. So that's an indication that this isn't good. And it was, I think the other one was, yeah, X3 to X7. Those are the ones. And you see the way I've got these, that really highlights those well, that highlights these well. So I just found, I made up my own thing to just help me see what were the collinear pairs. But what I do, I still looked at with 6 features and with 7 features, thought, what is that? But then, sorry, did I run that? Yeah. granite. Sorry, I hope I'm not confusing y'all with my excessive scrolling there. So what am I doing here? Now let's compare accuracies of models that trained with X1 through X6, X1 through X7, and X1 through X5, the known best model. Again, just showing that, okay, the accuracy is getting better. And here is the X5, and that has the worst accuracy. Not by a lot, but again, don't let that complicate things. So this new experiment that we just did with all 7, we're just going to run through the stuff we were just talking about. Here's the real model. I'm adding the noise. I'm putting it all together. And I'm using more NumPy now. And I've got my correlate. I adjusted my colors just so I could see things more clearly here. Here's my collinearity. I'm doing my new adjusted measures to give me more visibility. And sure enough, I get indications of not good things. But still, I use this trick of running through one removal at a time. So I first find that it is clear that we need to do comparative elimination among X3, X4, and X7, and then X1 and X6. So how do I do that? I'm just going to look at those R-squareds again, now that I know that. And I still just run through them all. Okay, clearly I can't remove any of these, but now it's between these. Well, which one is the worst accuracy among those? And so I decide it's best to remove X7 from looking at these values. And then the next one, so I do that, and then I start all over again. And I look at what I've got remaining, and now I cycle through the remaining of them, and I can see that it's best. This is when X6 is removed, so it's better than when X1 is removed. So I know to remove that, and then we just do a final check to make sure we have no collinearity, which we don't. So the hyper summary is that don't get sucked into accuracy when you know collinearity is present, but compare accuracy, the accuracy that's highest with one removed, that's the one you remove. This is, and again, this was kind of almost the end of feature reduction with the spirit of collinearity alone. Now, let me, while I'm going to do this, well, I'm going to move a copy of this to our folder, but are there any questions at this point? Hey, Menha.
Hey, good morning. How are you?
Really glad you came, buddy. You're already being very giving to the family with your expertise and your knowledge. We really appreciate it.
Thank you for saying that.
Yeah. Was there any point that's confusing or I could make clearer? Help me help you, everyone.
Yeah, I guess this actually boils down to what variable you have at the end, right? So I can see 2 different scenarios, right? So one of them is more like proxy variables. So a lot of times, the kind of variable you can measure is not actually the actual variable you are interested, right? So something like latent construct almost, right? As an example, the real variable you want to measure might be reliability, right? Well, you cannot really directly measure reliability. You're going to build some proxy variable from the data to trying to capture, right? And by definition, those will be highly correlate among each other because they are capturing the underlying reliability dimension, right? So in that case, what also can be used instead of this would be factor analysis or a dimension reduction technique. Then essentially you're trying to load the set of variables x through x1 through x3, saying that those are supposed to load onto underlying reliability. Then you can factor load this onto the reliability and then using the factors as a regressor instead of the variable itself, right? That's another way of achieving something similar, but all depending on what you are trying to measure, what is the relationship between the variables, right?
I believe you, if I understood you correctly, I believe you're right. And it brings up another point in my mind. It's this. What would you do first? Would you seek to remove collinearity first or unimportant features first? I think if you use, I'm glad I got a smile out of Guy, because it's not an easy question to answer. But here's my current inclination is this, guys. All right. The p-value analysis is so powerful and that it is safe to go about removing features using the p-value analysis first and then focus on the collinearity. But from everything I've seen experimentally so far, I love the p-value analysis even more than the lasso now. And I'm really kind of surprised to say that. But once I show you all the lasso, you'll see why it's very popular too. And but then there's this other question. And Garth and I agreed that it probably doesn't matter, but we're going to run an experiment just to prove it to ourselves. And it's this. Should you do feature engineering first and then go through all of this stuff like reduction and collinearity and all of that? And our current best guess, because we've never seen anyone state this, is do feature reduction and collinearity removal on your original features and then go into feature engineering. But can we say definitively that's best? No, it's just that our guts are telling us that. Because feature engineering can get quite complicated with the number of extra features you can throw in, depending on the order of how many orders of power you're using in your feature engineering, or I should say adding polynomial features, which is the most common way to do feature engineering when you're not sure what feature engineering to do. So it's a spirit of why complicate the feature engineering with collinearity and unimportant features present when you could just get rid of them first, then do the laborious exercises of feature engineering. I hope that makes sense. Some of these things, I remember I'd hear my professor say something, and 5 to 10 years later, I'd be working with something, thinking about something, I'd go, oh, then it would all of a sudden make sense. So if you didn't understand what I'm saying now, hopefully anywhere from 5 minutes to 50 years from now, it'll make more sense. All right, any questions before we take a break before mentoring? I hope this was valuable.
Thank
I
you.
feel like it was an outstanding lecture, but that doesn't really matter what I think. It matters how much of it got into your heads. That's what matters to me.
Maybe jokingly, I think the VIF function is currently not in the scikit-learn. Maybe your open source contribution opportunity, just submit to include VIF and scikit-learn or stat models in Python, right?
Now say that, which
Yeah, I don't
function in
think the
scikit-learn?
variance, yeah, the VIF, the variance inflation reduction analysis, right? That I don't think there's a built-in function in scikit-learn yet. Also, maybe not in stat model. So your
I-
open source contribution kind of opportunity, I guess.
Yeah, I would, well, actually, Minha, you might have came in late when I said this. I don't really find those two things very valuable. In fact, I would rather use my correlation-based tolerance and variance inflation factor
I
over
see.
the R squared versions of them, because it's actually harder to do the R squared versions. And they're not, in my opinion, telling you enough more than what you were told by the correlation matrix. So I'd rather just apply those same types of calculations to the correlation values in the correlation matrix, and then use kind of adjusted guidelines from that. That's what I was saying earlier. I just don't really find tolerance and variance inflation factor very helpful. Because
Yeah,
in
makes sense.
the end, it just, all of those things, correlation, tolerance, variance inflation factor, they just tell you if you still have collinearity present. But the correlation matrix at least tells you which pairs you need to test against each other to see which one needs to go.
Yeah, regarding the dimension reduction technique is actually more telling. It actually load onto correlation, right? So you can actually use your correlation to do PCA as an example. You can either use correlation or covariance to do dimension reduction. That actually tells you a lot. What is the underlying dimension and what variables actually matter for the overall variation, right?
Absolutely. But what I found is if you go into the PCA space, the eigenspace, what's interesting is, yeah, it'll remove collinearity, but it also tell you which PCA features are not important. But then if you try to translate those reduced PCA features back to the original space,
that's usually very difficult.
You get all the collinearity back. So it's still better parsimony wise to go ahead and if it's not too hard, identify your collinear features and remove the one that whose removal contributes to improved accuracy the most. So, all
yeah,
right,
actually, this is really studied well in the psychology for the measurement theory. So there are concept of measurement and then truth and the error kind of relationship and reliability. So they actually have some suggestion about how to go about this kind of problem. It's all depending on actually conceptual and causal relationship, more like causal graph, right? So actually sometimes it's better to think about conceptual kind of angle rather than data angle, right? That actually also clarifies what kind of relationship should exist, or some relationship is just, noise, right?
Yeah, good points. Okay, I need a little bit of bio time before mentoring, so I'll see you all over in mentoring. Thanks for attending, guys.
Okay, yeah, nice kind of cool.